And we are back with 7.5 today. Hope y'all are doing well. We are going to talk about dividing with radicals and specifically rationalizing that denominator, making sure there are no radicals in the denominator, not only square roots now, but nth roots. So just as a review, right here we have the square root of 12a to the fourth over b to the fifth. If we were asked to simplify this, and we always should simplify when we can, first step I would advocate for is, okay, well, let's split it up, top and bottom. Square root of 12a to the fourth over square root of b to the fifth. So, okay, square root of 12a to the fourth. I'm going to come up here and say 12 is 4 times 3 is 2 times 2. Again, we're looking for groups of 2 because it's a square root. We talked about that a lot in 7.4. So group of 2 right here. So it looks like the top could simplify to 2 square root of 3. That 3 didn't have a pair, a group of 2. And then we had a to the fourth. How many groups of 2 can we make? 2 groups of 2, nothing left over. So 2a squared root 3 over square root of b to the fifth. We have 5 b's. Here's a group of 2. Here's a group of 2. 1 left over. So it looks like the square root of b to the fifth. 2 groups of 2, so b squared root b. So that's simplifying. That's okay, but remember we don't want any radicals in the denominator. It's not simplified if there are any. So how have we rectified this in the past? How have we fixed it? I'm going to multiply both top and bottom by root b. Because now we do have a group of 2 b's on bottom. I'm looking at the bottom, I'm saying we have this root b, but we also have this root b. We have 2 of them. They can form a group of 2, and they can kind of break out of that radical. So what do we get? We get 2a squared root 3b. I'm going to combine those things inside the radical, as we usually do when we're multiplying, over, it looks like b squared, and I'll show every step, root b squared. Just like I was saying, we combine them. And so really, what does this turn out to be? 2a squared root 3b over, this looks like b squared times the square root of b squared, which is b. We're going to call that b cubed. We can pull one more b out of that root b squared. So b squared times that one more b, b cubed. And now we don't have any radicals on bottom, which is kind of where we want to be. So square root of 12a to the fourth over b to the fifth looks like 2a squared root 3b over b cubed when all is said and done. Let's do another one. This one is just numerical. Root 14 thirds. Well, I'm going to have to say that's root 14 over root 3. 14, if we try to simplify it, 2 times 7, and those are both prime, and there are no groups of 2, so that's actually as far as I can go. I can't simplify root 14 down at all, nor can I simplify root 3. But since I don't want a radical down there, I'm going to multiply by that root 3 over root 3. So 14 times 3 on top is root 42 over root 9, because we multiply the insides. And what is the square root of 9? 3. 42, if you were wondering, can we simplify that? Well, that's 3 times 14. We know that's 2 times 7. There are no groups of 2, so we can't simplify. So final answer here, root 42 over 3. And one thing I just want to kind of help you out with, a little bit of a shortcut maybe. Root 3 times root 3 is definitely going to be 3. we kind of hit that hard for semester. So root 3 times root 3 is going to be 3. You don't always need to show this middle step of, oh, it's root 9. Because why are we doing this? So that we can just get 3. We can get rid of that radical. So root 3 times root 3 is definitely 3. There we go on this one. All right, so one more that looks a little bit different before we talk about a concept. We say, okay, 7 over 4 minus root 3. And I say, okay, well, there's only one radical there. And unfortunately, it's on bottom. So I will go ahead and just multiply by root 3 over root 3. And that should fix the problem, right? So on top, we get 7 root 3. On bottom, we get 4 root 3 minus, and then root 3 times root 3 is just 3, we said. Awesome. So we fixed that radical. But you notice, hey, we've got a 4 root 3 here now, which is an issue. So naturally, I mean, we would say, okay, let's multiply this by root 3 over root 3. That'll get rid of that root 3 in the first term on the bottom. So 7 root 3 times root 3. Well, the root 3 times root 3 is just 3. So that's like 7 times 3 over 4 root 3 times root 3 is similarly 4 times 3 minus root 3. So 21 over 12 minus 3 root 3, excuse me. And hopefully by now in this example, you are seeing the issue with this strategy. At first, we got rid of the radical on the second term on bottom. We made it just 3, but in doing so, we introduced a radical to the first term. And then when we multiplied by root 3, we got rid of a radical on that first term, but we reintroduced it to the second term. And we could keep going and going and going, and this will flip-flop forever, but this is not good. This is an issue. We will never end up without a radical in that denominator. So what was different? Why didn't it work this time? Well, what was different is that there were multiple terms on bottom. There was a 4 minus root 3. In the previous 2 examples, it was just b to the 5th on bottom, or 3, no pluses or minuses, just one term. We can see when there are multiple terms, we have kind of an issue here. So how do we solve that issue? With conjugates. Now, most recently, you have seen this when we were talking about complex conjugates with imaginary numbers. What's the conjugate of 4 plus I? 4 minus I. We said just flip the sign of that imaginary part. Really similar here. We are looking at the radical conjugate. The conjugate of A plus root B is A minus root B. And the conjugate of A minus root B is A plus root B. So we're just flipping the sign of that radical part. So to rationalize, and here's the money statement, to rationalize a denominator that is in the form A plus root B, we are going to multiply top and bottom by the denominator's conjugate. Let's see it in action on that problem that we just were going in circles on. 7 minus 4 root 3. Well, 7, I completely misspoke there, sorry. 7 over 4 minus root 3. 7 over 4 minus root 3. If we're going to multiply top and bottom by the radical conjugate, that would be 4 plus root 3. Flip the sign of the radical part. Okay, let's see what happens. I'm going to do the bottom first because that's the part we really care about. We want to make sure we don't have a radical down there. Let's FOIL. 4 times 4 is 16 plus 4 root 3 minus 4 root 3 minus, and what is root 3 times root 3? Just 3. And I think we're good because it looks like we have radicals there, but plus 4 root 3 minus 4 root 3. Our whole denominator is going to be 16 minus 3, or 13. This is how multiplying by that conjugate fixes the issue. Let's multiply the top. 28 plus 7 root 3. So final answer, 28 plus 7 root 3 over 13. No radicals on bottom in sight. We solved that. I want you to try this one. A little bit harder. There's a radical on top, so you'll have to do some radical arithmetic up there. But try this problem and then unpause your video and see if you got what I got. All right, so there it is with my work on the screen. You can see I multiplied in blue on that problem by 3 minus root 7 on top and bottom, the conjugate of my original denominator. And when we FOIL everything out, you can kind of see my work there. On bottom, we had minus 3 root 7 plus 3 root 7. Those canceled, so I ended up with 9 minus 7, or 2. And on top, when we FOILed, we got 12 minus 4 root 7 minus 3 root 7s plus root 7 times root 7, which is just 7. So combining those like terms, we ended up with 19 minus 7 root 7 over 2. So I'm hoping your work kind of came out to the same. Pause it and compare our works if it didn't. See if you can find the difference. But there's one more thing we have to talk about on this video. What if it's not a square root? What if it's an nth root in the denominator, a third root, a fourth root, a fifth root, a 10th root, any numberth root? How do we handle that? Well, here's the idea, and you want to be kind of really paying close attention right now. If I have the cube root of 13b squared over a, I'm still going to split it up top and bottom. I'm still going to say, well, cube root of 13b squared over cube root of a. Cool, awesome, great. But right here, do I want to just multiply by cube root of a? This is one, we don't need the conjugate, it's just one term, a monomial. But I'm here to tell you this is not going to do it. And this is where I said pay attention closely. This will not get rid of the radical on bottom. It's a cube root. We're looking for groups of 3. How many do we have right now? 1, 2. This is what we're going to need to do. That's what we're going to need to do so that we have 3. It's a cube root. We're looking for groups of 3. That is going to turn the bottom into just a. Because, and I'll show kind of it fully here, on bottom, this will give me the cube root, and we can combine everything inside those cube roots we're multiplying. Cube root of a cubed, and on top we have cube root of 13a squared b squared. And then one more simplification, cube root of a cubed on bottom. Now I have my group of 3. I can just write that as a. Cube root of 13a squared b squared. But the big takeaway here is the fact that, look, we can't just multiply by 1 cube root of a on top of bottom because we're looking for groups of 3 because it was a cube root. We had to do it twice. Now we have 3 total. Now we got rid of that radical on bottom. Okay, so right here, it's a 5th root. Okay, awesome. 5th root of 3 over 2x. Well, top and bottom, I'm going to get 5th root of 3 over 5th root of 2x. I need to multiply this how many times? I need a group of 5. Currently, I have 1. I'm going to multiply this by 5th root of 2x. And that almost looks like 5 root 2x. I'm going to make it smaller. 5th root of 2x over 5th root of 2x. That'll get me 2 of them. Here's 3 of them. Here's 4 of them. but I needed a group of 5. Here's 5 of them. And so what is this going to give us? Well, on bottom, we know that this is going to equal, and I'm going to skip some space here, and there's a reason. This is going to equal 5th root of 2x to the 5th, because we're multiplying all of them together. There were 5 of them. And up here, we're going to get 5th root of 3, 2x to the 4th, right? Because 2x, 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 2x. There we go. And so on bottom, 5th root of 2x to the 5th is just 2x. On top, we could write that as 5th root of 3, 2 to the 4th. Let's just simplify that exponent. 2 times 2 times 2 times 2 is 16. X to the 4th. And so to close up shop for the day, 5th root of 3 times 16, 48 x to the 4th over 2x. Whew. Okay, that one was kind of a lot. A 5th root, and especially you might be thinking, man, that's a lot of writing up there. What if it was a 10th root? Do I really have to write it 10 times? The answer is kind of no. I'm going to show you another way we could have written it, and a way that I will kind of recommend. What if we just wrote it as 5th root of 3 over 5th root of 2x, that's our original, times 5th root of 2x over 5th root of 2x to the 4th power. That's basically what the blue part says, right? That's the definition of a power, times itself that many times. A lot less writing, and we still see we need our group of 5. Here's 1, here's 2, 3, 4, and 5, because there are 4 of them there. And then we can just solve it the rest of the way. It'll come out exactly the same. 16x to the 4th inside that top purple multiplied by the 3. We'll get 48x to the 4th inside that 5th root all over 2x. And one last thought, oftentimes I get a question, x to the 4th on top, x on bottom, can't we cancel those? No, because the x to the 4th is inside that radical. So we can't do any canceling. Same with the 48 over 2. But guys, there you have it. That's kind of a tough example I wanted to leave you with. But if it's an nth root on bottom, we have to multiply enough to get a group of n. On the top one on the screen, there's a cube root, so we needed to multiply by 2 more cube root of a's to give us 3 total, group of 3 for the cube root. On bottom, we had to multiply by 4 more 5th root of 2x's to get us a group of 5 total. So practice some of these dividing with radicals on bottom. Sometimes there'll be square roots, cube roots, sometimes there'll be nth roots, and that's kind of my catch-all to say anything. If you have questions, let me know, reach out to me, or circle them so you can ask them next time we're in class together. But definitely do practice this, and we will be back next time with 7.6. So until then.